Good afternoon everyone. Today we are going to study about the wedge shape film. Wedge shape film. Now first of all, how the wedge film are obtained? We are considered the two glass plates. That two glass plates inclined with a small angle as alpha. Suppose O x and y. We are consider O x and O y are the two glass plate. In between two glass plate, we are inserting the very thin wire or a paper of sheet, and there is a formation of a air wedge between these two glass plates. The inclination is very small, like a alpha, because the two plates are in a contact at point O, and air wedge can be formed in between the two glass plate OX and OY. OX and OY, the thickness at the point O is 0, and the thickness of the air film goes on increasing from the opening end where we are inserting the paper sheet of paper or a thin wire or our hair, and that type of air wedge is known as a wedge shape film. Film produced due to the air wedge, so which is known as a wedge shape film. Now these wedge shape films we are used for testing the flatness of the plates, as well as we will use to measure the thickness of a air film or thickness of a paper sheet, those we are inserted at the one end. That purpose we will use the wedge shape film. Now the experimental arrangement of this wedge shape film. Here we consider the source of monochromatic light, one lens, inclined at 45 angle to the glass plate, Now the experimental arrangement of the wedge shape film. Here we consider the sodium source as the monochromatic source. It consists of the single wavelength, that is why it is known as a monochromatic source, which is incident on the condensing lens. That lens we will use. The scattered beam can be converted into the parallel beam. That conversion for the parallel beam we will use here the lens, and that lens is in that parallel beam inclined at 45 angle to the plain glass plate. Now here this angle made by this ray is nothing but 45 degree, and these 45 inclined these rays are partially reflected and partially refracted. Those rays are reflected, they are inclined at normal to incident to the wedge shape film, exactly normal to the wedge shape film. Now here this whole system again we are consider as a air wedge film, and which is a plain and transparent. So here there is a formation of partial reflection, refractions and the interference pattern. Now here these rays are incident normally to that one, so the reflection angle is nothing but a 0. When the rays are incident normally to the any thin film, then the reflected rays having the angle of refraction is a 0, so cos 0 we will consider as a 1. Now here these rays at the glass plate, they are insert inside the air film, so there is again the partial reflection and reflection, and inside the film again suppose we consider this ray, there is a reflection inside the film, refraction and multiple reflection inside the film, and comes out of or rays are emerged out. Now here we observe that there is a formation of a two rays. when the two waves are superposition to each other, there is a formation of a interference pattern. Now, here these rays are incident normally in a downward direction and those rays are partially refracted, rays are in the upward direction. So, both the waves are superposition to each other or superimposed to each other, then there is a formation of a interference pattern due to the air wedge. Now, those interference patterns we are observed under the travelling microscope by using the air wedge. There is the alternate dark and bright fringes are observed or the bands are observed, and each band having a equal thickness as well as distance of separation between the each band is nothing but equal. And these phenomenon we will use to test the flatness of a glass plate or flatness of a lenses. We will use this phenomena for a air wedge film. Now, those rays are reflected and transmitted. For that one we will use to calculate the part difference between that one. For calculations of a part difference, we will consider the ray diagram for that one. For calculation of path difference. For that one we will draw the one ray diagram. Suppose these are the x and y, OX, OI inclined with the small angle as alpha. These rays are incident to that one. Internal reflection take place and emerge out. Now, draw the normal. Here also one of the normal we will draw, and the rays are meet at a normal point. Suppose this one is a R, this is R plus alpha. Now, for calculating the value of part difference, we have to construct the diagram, draw the two perpendicular, one is here and the second one for the second reflected light. Now, here suppose A, B, C, this D, one normal first is E, and suppose this one is N, this is I and this one is a J, and K and L, suppose we are consider the two reflected light. Now, according to the geometry, this one is angle of incident, this is angle of refraction. So, this is also the angle of incident, this is also the angle of refraction. And now, our aim to find out the part difference between these two reflected beam by using a wedge shape film. Here we consider OX and OY are the two parallel glass plate inclined with a small angle as a alpha. Then we will incident a monochromatic ray AB on this one edge, one surface of a glass plate OX. At point B, the rays are partially reflected along the direction BK and partially refracted along the direction BC. At point C, again the multiple reflection inside the film is take place along the direction CD, and for calculating at point D, where the rays are emerge out along the direction DL. So, we will get BK and the DL are the two parallel reflected ray, and our aim to calculate the part difference between these two parallel reflected ray. Now, for calculating the values of parallel part difference between these two parallel reflected ray, we have to construct the figure. We draw the two normal DE on the BK as well as DN along the BC inside the film. Now, according to the geometry, suppose this angle is a R, this one is also the R, and this angle is also the R. This is angle of incident, this one is also the angle of incident. Now, here we will get for the next at the point I and the j, both are nothing but the reflected rays we are meet at a single point I as well as a j. Now calculate the path difference between these two reflected rays. Delta is equal to the path difference, generally we are denoted as a capital delta. Delta is equal to the path difference in air and minus of path in the path in the media minus path in the air. So delta is equal to path in film minus path in the air. Now here path in film, we will consider this path BC plus CD as a path in air, a path in the film and a BE in the air medium. So the for refractive index in the film as a mu, we will consider path in air film BC plus CD minus path in the air is nothing but BE. In the air we consider that value of mu is nothing but 1. So we are not consider here BE as a 1, denote the equation number 1. After that our aim to find out the value of BE by producing the normal or drawing the normal on the two reflected light BE, BD, DE as well as BN on corresponding BK and BC. Now for calculating the value of BE, here this angle of incident we are consider as BDE as angle of incident, angle BDE, BDN as the angle of refraction. According to the Snell's law, we know that mu is equal to sine of I upon sine of R. That is the refractive index of a glass or media is equal to sine of I upon sine of R. Now in this triangle BDE, this D angle as a I, so sine ratio is opposite side to the hypotenuse, opposite side is BE upon BD divided by sine of R, sine R is again opposite side to the hypotenuse, opposite side is BN divided by the BD. Now BD get cancelled, remaining only BE upon BN. So the value of BE equal to mu times BN and denote equation number 2. Now we substitute the value of BE in equation number 1, we will get the path difference delta is equal to mu times BC plus CD minus of mu times BN and denote equation number 3. Now here our aim to calculate the value of BN, or we have to cancel the value of BN by using the path difference in the film. Now for according to the construction here we observe that the value of CD, that is a path in the film, the length of the path in the film is equal to the length those extended at the outside area. So the value of CD is equal to the value of CR, or the length of CD is nothing but length of CR, but CD is equal to CI. So we will get mu times BC plus CI minus of mu times BN. But what is a BC plus CI? This total length is nothing but a BI. So this value B is mu times BI minus mu times BN. Now BI, thus total value of BI we can write in the form of addition of this BN plus NI. Now why we are added that one? Because our aim to cancel out the factor was a mu times BN. So which is equal to mu times this BN plus CNI, BN plus CNI minus of mu times BN. Now here mu times BN get cancelled, remaining factor as only mu times NI and denote equation number 4. Now our aim to calculate the value of Ni for calculating the effective part difference. For that one we will consider this bigger right angle triangle, because this one is a normal, that is why this angle is a right angle triangle, and this big right angle triangle we will consider, that is a DIN or NID, that right angle triangle we will consider. In a triangle DIN, now our aim to calculate the value of Ni, so we will consider the ratio between these two sides Ni as well as the Di. In Ni and Di, this angle is r plus alpha, so the relation between that one is nothing but adjacent side to the hypotenuse. Adjacent side to the hypotenuse ratio is nothing but a cos ratio. So cos of r plus alpha is equal to Ni upon this value as a Di. So we will get the value of Ni is equal to Di into cos of r plus alpha. But the Di is nothing but this total distance, this distance or the thickness of the air film is a G, air film is nothing but a T, and the same distance we can extend it in a backward direction as a T. So Di is equal to Ni is equal to 2T cos of r plus alpha, and here denote that equation number 5. And we will substitute this value of Ni in equation number 4, or then the value of delta we will get 2T cos of r plus alpha and the mu as it is. So we will get 2 mu t cos of r plus alpha. This is the part difference between the two parallel lines. But here in a wedge shaped film there is a partial reflection and refraction take place from denser media to the air media or the rarer media. That is why when the reflection from denser media to the rarer media, there is a abrupt phase change of pi reverses is take place, and that phase change of a pi is equivalent to the part difference of lambda by 2. So that in case of, for calculating the value of effective part difference, we will add as well as subtract the part difference as a lambda by 2. For that one, delta is equal to 2 mu t cos of r plus alpha plus or minus lambda by 2. This is the effective part difference for the two reflected rays in a wedge shaped film. But here we are consider as a r plus alpha. Alpha angle is very small, so that the cos alpha, that value is considered as a 1. So the effective part difference for the two reflected rays in a wedge shaped film is nothing but 2 mu t cos r plus or minus lambda by 2. This is the our effective part difference between the two reflected rays in case of a wedge shaped film. Now there is a condition for a maxima and minima. For condition for maxima, condition for maxima means the intensity is maximum. So which type of fringes we will get? That are nothing but the bright fringes, and that bright fringes, when we will get the value of part difference is the integral multiple of lambda by n lambda, that is integral multiple of wavelength. So we will get the value of delta is 2 mu t cos of r plus or minus lambda by 2 is equal to n lambda. So 2 mu t cos r is equal to 2 n plus or minus 1 lambda by 2. Similarly, we can calculate the condition for a minima. For minima, the value of delta is nothing but odd multiple of lambda by 2. When the odd multiple of lambda by 2 delta value, so we will get 2 mu t cos of r plus or minus lambda by 2 is equal to 2n plus or minus 1 lambda by 2. So, 2 mu t cos of r is equal to n lambda. Suppose this is the equation number 8 and this one is equation number 9. Whenever the condition mu t cos r is equal to n lambda is satisfied, then we will get the dark fringes or the dark band, and whenever the condition of equation number 8 2 mu t cos r is equal to odd multiple of lambda by 2, then if this condition is fulfilled, then we will get a bright band, and the fringes according to that one equal thickness of equal distance of separation are find out alternate dark and bright according to the conditions of a dark and a bright, dark and bright, we will get the alternate dark and bright fringes. Here the value of n's are nothing but starting from 0, 1, 2, 3, 4 etc. as well as for the dark also the value of n is nothing but 0, 1, 2, 3, 4. Then we will find out the alternate dark and bright fringes. In this way we can calculate the path difference in a wedge shaped film.